In this video, we're going to talk about calculating work. So work is done by a force when it moves an object. And if the force applied is constant, meaning it stays the same throughout the entire motion of the object, then we can use the following formula. We can say that work, if an object is moved a distance d in the direction of an applied constant force F, then the work W done by the force is defined as W equals F times d. So the force times the distance. So for example, if I wanted to determine the work done by a constant force where an electric hoist, for example, lifts a 2,500 pound car 6 feet, my F, the amount of force, would be the 2,500 pounds because that's what's being moved, and the distance would be 6 feet. So the amount of work done would be 2,500 times 6, which is 15,000. And then for units, we just kind of put a cross between the two units here. We call those foot-pounds. You do not need to change these over to joules or whatever you've done in a physics class. We just leave it like that. Another example says the locomotive of a freight train pulls its cars with a constant force of 9 tons, a distance of 1/2 mile. So F would be 9 tons and D would be 1/2 of a mile. So the work would be 9 times 1/2, which is 4.5. And we'll just call that mile tons. Again, there are official units that physicists like to use for the amount of work, but we're just going to keep it simple. So if you're answering questions in WebAssign, make sure you check what the units are expected to be when you enter the problem. If it's anything other than the units that you started with, you may have to do a conversion like from inches to miles or feet or something like that. But it should be pretty straightforward. Now, whereas work done by a constant force is a very, very simple multiplication, when a variable force is applied to an object, calculus is needed now in order to calculate the work done because the amount of force is going to change as the object changes position. So some examples of this: if you take a spring like a slinky and you compress it, the more you compress it, the more force is required to compress it. Or if you're picking up like a chain that's laying on the ground, the more of it you pick up, the more weight you're having to hold because the ground is no longer supporting it. So that's what we mean when we say a variable force. So to derive the formula we need, we're going to consider an object moved along a straight line from x equals a to x equals b by a variable force f of x, and this is an example of what that might look like. It's just being moved an amount of delta x here. We're going to let delta be a partition that divides the closed interval from a to b into n subintervals, like so. Those intervals will be something like x of 0 to x of 1, x of 1 to x of 2, all the way down to x of n minus 1 to x of n. And delta x is just the width of each interval, so x of I minus x of I minus 1 for any I. And we're going to choose c sub I to be a point in between those two, x of I minus 1 and x of I, where f of c sub I is the force at that point. So we're basically going to estimate this work by looking along all of these subintervals and multiplying the work times the distance. So the force times the distance. So this is the force and this is your distance. So if we consider infinitely many subintervals, so that you're looking essentially at those intervals getting tinier and tinier, so it's closer and closer to the actual amount of force at each point, then you think of this as an integral from a to b of the f of x dx, because this is your delta x and this is your f of x. So we're just going to integrate it. There are 3 basic laws of physics which drive most of these problems, and they form your equations for f of x. The first one is Hooke's law, which says the force required to compress or stretch a spring within its elastic limits is proportional to the distance that the spring is compressed or stretched from its original length, so F equals k times d. And there is some kind of a spring constant of proportionality K, which will depend on the specific nature of the spring. So you'll be given information to calculate that and then plug it into the formula. There's Newton's law of universal gravitation, which says the force F of attraction between two particles of mass m1 and m2 is proportional to the product of the masses and inversely proportional to the square of the distance between the two particles. So you've got your G, which is a value, the gravitational constant, so that may be in something like this one, which is in cubic meters per kilogram second squared. But in this case, you're still going to multiply that G times m1, m2 and divide it by d squared. So that's where the proportionality comes from. And then this law says the force between two charges Q1 and Q2 in a vacuum is proportional to the product of the charges and inversely proportional to the square of the distance between the two charges. So notice this is very similar to this one. We've just got different letters. So you're going to see that a lot of the applications are going to come from something similar to one of these two. This is one of the classic spring problems. It says a force of 5 pounds compresses a 15-inch spring a total of 3 inches. How much work is done in compressing the spring for 7 inches? So the first thing we recognize is this is a spring, so we're going to be using that first law, F equals K times D. That was Hooke's law. And we know that we're going to consider this to be F of X equals K times X, which is going to be equal to the amount of force required to compress the string, or the spring, sorry, X inches. So we're given a couple pieces of information. We're given kind of an ordered pair, if you will. A force of 5 pounds compresses a 15-inch spring, a total of 3 inches. So it's not really an ordered pair, but it's enough information. So what this allows us to do is figure out what K is for this spring. So the first thing we always want to do with these problems is find K for this spring. And we know that the force is equal to 5 pounds when the amount that the spring is compressed, X, is equal to 3 inches. They throw that 15-inch in there to just kind of throw you off. You don't actually need that information in order to solve this problem. So based on this, I know that 5 is equal to K times 3. And if I solve that for K, I get K equals 5/3. So that tells me that for this particular spring, F of X is equal to 5/3 X. Now we want to know how much work is done in compressing the spring 7 inches. So now that we have our function set up, we know that work is the integral from a to b of f of x dx. And for this particular problem, we want to go from 0 inches compressed to 7 inches compressed. So this is going to be the integral from 0 to 7 of 5/3 x dx, because 5/3 x is our f of x. So we just need to integrate this. So we'll have 5/3 times x squared over 2 from 0 to 7, or 5/6 x squared from 0 to 7. And when I plug in my bounds, I get 7 squared minus 0 squared times 5/6. And 7 squared is 49 times 5/6 gives me 245 over 6. And our force is in pounds and our distance is in inches. So we're going to call those inch pounds. Now, if it said foot pounds on your answer sheet, or when you're answering in WebAssign, then you would want to convert from inches to feet before you start the problem. So just be careful about that kind of thing. Make sure you're paying attention. This example says a force of 250 newtons stretches a spring 30 centimeters. How much work is done in stretching the spring from 20 centimeters to 50 centimeters? So again, we've got our given piece of information. We know that F equals 250 newtons, and newtons is a measure of force, when X equals 30 centimeters. So this is a spring. F equals k times x. So 250 is going to be k times 30. And if I solve for k, I get k is 250 over 30, or 25 over 3. So f of x is going to be 25 over 3x. And then we want to go from 20 centimeters to 50 centimeters. So you're starting at 20 centimeters and you're going to compress it the rest of the way to the 50 centimeters. So the amount of work done here is going to be the integral from 20 to 50 of 25/3 x dx. And this, of course, gives me 25 over 3 times x squared over 2 from 20 to 50, which is 25 over 6x squared from 20 to 50. And then if I plug in those numbers, I'll have 50 squared minus 20 squared, which gives me 25 over 6. That'll be 2,500 minus 400, so 2,100. And when I multiply those, I get 8,750, and we're using centimeters and newtons, so we'll have centimeter newtons. Wacky units here, but that's where we're going to leave it.